So I want to show you guys how to do a fairly complicated calculation, calorimetry calculation. And what came to mind was a documentary that I've seen called Touching the Void, about these two guys that climbed a mountain in South America, and they got into an accident. One of the guys broke his legs. They had to try to get down the mountain all by themselves. It's a really interesting documentary. If you have a chance, check it out. But one of the things I remember is that they had these little camping stoves, and they were trying to take the snow and heat it up and turn it into water to drink, which is a pretty common thing. You don't want to carry the water all the way up the mountain. It's really heavy. So you bring these little burners, you can put the snow in there and melt it and drink that. So what I want to do is try to figure out how much of this fuel they would have had to burn to produce a certain amount of water. So let's say the question is, how many grams of propane must we burn to turn 1,000 grams of snow at, that's probably pretty cold up there, let's say it's minus 15 Celsius, into drinkable water at, let's say, 15 degrees Celsius. Okay, so we're using the energy from the combustion of the propane in order to heat that snow up, melt it, and turn it into water that's not going to be super cold to drink and give you hypothermia or something like that. So this is going to be pretty complicated, but again, it starts with this very simple equation that says that the change in energy of the universe has to be zero. So what that means is I lost my black marker. It's over here. We're going to have a change in energy for something that's losing energy and a change in energy for something that's gaining energy. So we could say the change in energy for the thing that's gaining plus the change in energy for the thing that's losing has to equal zero. Okay? So where's the energy going in? Where's the energy coming out? Well, the energy is going into the snow that we're trying to melt and turn into drinkable water. So I can say the change in energy for the snow, the energy is going out of the propane as we burn it and change the nature of the bonds. So the change in energy for the propane should balance that, and we should end up with zero. Okay? So now we have to think about, okay, well, how do we calculate those changes? So I'll start with the propane, because the propane is going to undergo a chemical reaction. We know C3H8 is going to burn in O2, it's going to produce CO2 and H2O. We're going to need a 3 here, we're going to need a 4 there, and then 5 there, if I did it correctly. Okay, now this energy change, we're going to break some carbon-hydrogen bonds here, we're going to break an oxygen-oxygen bond, and then we're going to form carbon-oxygen bonds and hydrogen-oxygen bonds. And this is an exothermic reaction. So we're going to start here, we're going to have some activation energy, and then we're going to end at some lower potential energy. Now the change in this process, which we call delta H, I looked it up. It's negative 2,200 kilojoules per mole. So for every mole of propane that we burn, it's going to release 2,200 kilojoules. So to calculate the energy change for the propane, we're going to use that delta H, and we're going to have to multiply it, since this is in kilojoules per mole, by how many moles we're actually burning. Now we're really interested in how many grams, but once we find the number of moles, we can use the molar mass to get back to grams. Okay, now what about the snow? Well, the snow is actually undergoing several different processes. If we go back to our heating curve for H2O, we have 0 Celsius here, we have 100 Celsius here. We know we can heat H2O up to its melting point, take some energy to melt it. We can heat it up to its boiling point. It takes some more energy to boil it, and then we could heat it up past its boiling point. And we know that each of these different regions of the heating curve takes a slightly different calculation. So here we use a Q equals mc delta T, and the specific heat capacity for ice, we're going to use 2 joules per gram per Celsius. Up here for water, that's another Q equals mc delta T because the temperature is changing, but the specific heat capacity of water, we're going to use 4 joules per gram per degree. Now this region here, where we're actually melting it, there's no temperature change, so we can't use mc delta T. We use Q equals delta H times N, where delta H is the change in enthalpy associated with melting the ice. We call that delta H of fusion. And for ice, it's about 6 kilojoules per mole. All right, so since we're starting with ice at -15 down here, we have to first calculate how much energy it takes to heat the ice up to the melting point. Then we have to calculate how much energy it takes to melt it, and then we have to calculate how much energy it takes to get it up to 15 degrees Celsius, where we want it. So really, for the delta E for the snow, we're going to have Q for the ice, plus Q for melting, plus Q for the water. So 3 separate calculations here. And I've explained what we need to do to calculate those. The ice is going to be mc delta T. The melting is going to be delta H of fusion times N. And the water is going to be another mc delta T. Okay, so pretty complicated equation, but just a bunch of numbers that we're going to plug in. As long as we plug them in correctly, the math isn't all that hard. So where's my problem? We're trying to go 100 grams of ice. So the mass for the water and the mass for the ice is, sorry, it's 1,000 grams. The mass is going to be 1,000 grams. For the ice, I'm going to use the heat capacity for ice, which is in the board that I just did. And now again, we got to be careful. What is the temperature change for the ice? Well, the ice starts at -15, but ice can't exist above 0 degrees Celsius. So the temperature change for the ice, the final temperature is 0 Celsius. The initial temperature is -15 degrees Celsius. So the temperature change is actually going to be +15. So this calculation will give us the energy required to heat the ice up just to its melting point. Then we got to melt it. That's a delta H of fusion, which I said was 6 kilojoules per mole. Now we got to be careful because this is in joules here. So I want to actually convert 6 kilojoules to joules. That's 6,000 joules per mole. And then I have to be careful to make sure to multiply by the number of moles. That's 1,000 grams divided by the molar mass, 18 grams per mole. Okay, so this calculation will give us the energy required to melt the water. Then I'm going to add to that the energy required to heat the water up to the temperature we're going to end at, 15 degrees Celsius. So it's still 1,000 grams. The new heat capacity for water, we're going to use 4 joules per gram per degree. The final temperature of the water is going to be 15 degrees. The initial temperature of the water, remember water doesn't exist below 0 degrees. So the initial temperature of the water is 0 degrees. Okay, so all this, these are all just numbers, are going to allow us to calculate the total amount of energy required to go into the snow to get it to where we want to be. Okay, I'm running out of room here. Okay, whoops. But if we add to that the energy of combustion of the propane, which is -2,200 kilojoules per mole. So again, I'm going to change that to joules, so I'm all in the same units. Joules per mole times the number of moles. All of that should equal 0. So basically what I can do is, since I have all numbers and only one variable, the n, I can solve for the n, I can get a number, that's the number of moles of propane that it's going to take to release that amount of energy into the snow to turn it into drinkable water. And then I can take that number of moles, I can multiply by the molar mass of propane, and that'll give me the number of grams.